Greetings, differential equation scholars, and welcome to video number 3 in our sequence on applications of second-order differential equations. We've been looking at the motion of spring mass systems, beginning initially with the idealized situation of undamped motion. And most recently, in our second video, we started to take a look at the theory behind damped motion. What happens if we introduce additional forces into play? How does that change the equation of motion for the mass on the end of the spring? So what we're going to take a look at in video number 3 here is we're going to take a look at an example of some motion. We're going to start off with a review of undamped motion and solve an initial value problem. This will basically begin as a review of video 1. And then we're going to introduce an additional term into the mix and take a look at how that affects the motion. And we'll take a look at whether we end up with underdamped motion, overdamped motion, or critically damped motion as a result of the extra factor that we introduce. But let's begin here with a review. Never a bad idea to do some review of the material from section 5.1.1. Suppose we have a situation where we've got a mass that weighs 2 pounds, and suppose that when you put it on the end of a spring, it causes the spring to stretch 1.5 inches, 1/8 of a foot. And then suppose you take that mass and you move it to a position that's 2 feet below its equilibrium point. So you're stretching it down, and then you exert an initial upward velocity of 3 feet per second. You're launching it up at 3 feet per second as the object is released. We want to predict what the equation of motion for this mass on the end of the spring will be. To review, what we need to do first is we need to find two constants, k, which is the spring constant, and m, which is the mass of the object. To get the spring constant, we use the equation that F is equal to Ks. Remind ourselves here. F equal to Ks, that's Hooke's law. F, which is going to be the force, which here is the weight of the mass, that is 2 pounds. 2 pounds is equal to K times the displacement, and the displacement is 1/8 of a foot, or 0.125 feet. So when we solve for our spring constant K, we're going to find out that it's 16 pounds per foot. That's our spring constant. We need to know that. The other factor that we need, besides K, to figure out the omega for this system is the mass. Remember, mass and weight are not synonymous. We want to use our Newton's law, F equals ma, to discern what the mass is. If the weight is 2 pounds and the acceleration from gravity is 32 feet per second squared, then that means that our mass is really 2/32, or 1/16. And it's 1/16 of what we call in the English system, 1/16 of a slug. So now we know our K, we know our M. That will allow us then to get our omega squared. Remember that omega squared is the ratio of the K divided by the M. So it's going to be 16 divided by 1/16, which is 256. We're going to be using that omega squared value in just a little bit. Well, let's go and take a look at the differential equation that results here now. Went down a little too far there. Let's back up. All right. So the differential equation of motion, one way to write it, remember, is m times x double prime plus kx equal to 0. And you can always start off that way if you want, m times second derivative plus k times x equals 0. When you normalize that by dividing by m, you're going to turn that into the alternative form for the differential equation, which is x double prime plus omega squared times x equal to 0. And there's that omega squared of 256 that we were talking about a minute ago. That's a nice second order linear homogeneous differential equation with constant coefficients. It's got an auxiliary equation of m squared plus 256 equal to 0. And when we solve that for m, we're going to find that m is equal to plus or minus the square root of negative 256, which is really m equal to plus or minus 16i. So we have purely complex roots, actually say purely imaginary roots here. And so that's going to mean that we have a sum of sines and cosines, as we expect. Whenever we're doing a problem with undamped motion, that's what we're always going to have, this linear combination of sines and cosines. C1 cosine of omega t plus C2 sine of omega t. Here the omega is the square root of 256. It's 16. And so that means that our differential equation's solution is down here in the box, C1 times cosine of 16t plus C2 times the sine of 16t, coming from those roots of plus or minus 16i. Of course, that's the solution to the differential equation. What do we get for when we apply our initial conditions? Remember, one of the initial conditions was that we had moved the mass to 2 feet below its equilibrium position. And remember, coming down from equilibrium is in the positive direction. So x of 0 equals positive 2. And the other initial condition was that we were going to release it pushing upward with initial upward velocity of 3 feet per second. And so since that is a velocity in the upward direction, that would be an initial velocity of -3. So we have these two initial conditions. The first one is that x of 0 equals 2, coming from our initial position, and then also that x prime of 0 is -3, coming from the condition on our velocity. When we apply the first initial condition, that x of 0 is equal to 2, that's going to end up telling us, when you do the work on that C1, that constant equals 2. And when we do the second initial condition on the velocity, that's going to dictate that C2 ends up being -3/16. I haven't shown the work for that, but I'll leave that as an exercise to you to verify that. And so in the end, we have an equation of motion that says that our position is twice the cosine of 16t minus 3/16 times the sine of 16t. There we have it. Now let's take a look at, I've made some graphs here, and we're going to take a look at what the graph of that solution will look like. It's going to be an oscillating solution. And here we have it right here. You can see the oscillation around the equilibrium point as time goes on. Nice, smooth, oscillating motion back and forth and back and forth. If somebody asked us what's the amplitude of the motion, the amplitude here is, even though the mass starts out at 2 feet below equilibrium, the amplitude is actually ends up being slightly more than 2 because of the fact that we're applying that initial velocity at the beginning. The equation for amplitude, which you'll find in your text, says that the amplitude is the square root of the sum of the squares of the constants C1 and C2. So whatever you found those C1 and C2 to be, square them, add them together, take their square root, that's the amplitude. In this case here, it's the square root of 2 squared plus -3/16 squared. That comes out to be just a hair more than 2.009 approximately. So you can see what happens here after we release the object. We push it upward. It comes down, and it actually reaches a height that's about 2.009 feet above equilibrium. Then it returns back to equilibrium and then descends to a position that's about 2.009 feet below equilibrium. And it's just going to constantly oscillate back and forth between those extremes. You can see here I've written, this is the alternative form for the equation using amplitude and phase that your book talks about. If you'd like, as an exercise, you can investigate and verify that that's an alternative way of writing that equation of motion. What's the period? Well, remember that the period of motion is always 2 pi divided by omega. So here, omega was 16. So we have a 2 pi divided by 16, and that's pi over 8, which turns out to be about 0.393 seconds. So what that means is it takes about approximately 0.393 seconds for our mass, which was released, to go through one full cycle. So from the amount of time, for example, that it takes to go from this high point above equilibrium through its low point and then back to the high point again, that's going to be a total of 3.393 seconds, or excuse me, not 3.93, 0.393 seconds to go through one full cycle of motion from one position back around to itself again. Okay, so that's a review. That's doing some undamped motion, and with no dampening at all, we get nice oscillatory behavior. But we know that in the real world, that's probably not how a spring actually behaves. It doesn't forever keep going back and forth between the extremes. There's things like friction and air resistance that come into play. And so let's introduce a little bit more, you might say, reality into the situation. We're going to use the same problem, same scenario from the previous problem. But now let's suppose that we introduce a damping force that is exactly equal to the instantaneous velocity at the moment. In other words, we're going to take beta, that constant, to be 1 here. Some of the exercises in your book will say things like the damping force is proportional to 3 times the instantaneous velocity, or half of the instantaneous velocity. Here we're going to take it to be exactly equal to the instantaneous velocity. So our beta is going to be 1 here. And what that means is that our differential equation, remember, we have this new middle term, which is usually plus beta times x prime. So here it's just plus x prime. So the differential equation that was mass times x double prime plus kx equals 0 now has this extra term. So now we have 1/16 x double prime plus x prime plus 16x equal to 0. Now, when we normalize that by dividing by 1/16, or multiplying by 16, if you will, we also could express that as x double prime plus 16x prime plus 256x equal to 0. Now notice that's exactly the same equation that we had earlier, except for it's got this extra middle term here that's coming from the damping force. Instead of just x double prime plus 256x equals 0, we now have x double prime plus 16x prime plus 256x equal to 0. That's going to change our auxiliary equation. It's going to change how our solutions look like. Now notice in this case here that that coefficient of the middle term, once I've got an initial coefficient of 1 for x double prime, notice that the coefficient of x prime, which is now b divided by m, well, b was 1, m was 1/16, so b divided by m is 1 divided by 1/16, or 16. That's our coefficient in the middle, and we're taking that to be 2 lambda. Remember, the middle coefficient in our theory we call 2 lambda. So 2 lambda is equal to 16, which means really that lambda is equal to 8, and that lambda squared is equal to 64. in this case. Now that's very important because remember that the type of behavior we get from a damped system depends entirely on the relationship between lambda squared, which comes from the damping, and omega squared, which comes from the restorative force of the spring. Which one is stronger? Depending on which one's stronger, we're going to get either underdamped or overdamped behavior, or if they're the same, we might end up with critically damped behavior. In this case, we just found that our lambda squared was 64. But remember, we already know what omega squared is. Omega squared, and this doesn't change if it's the same problem and you're just introducing damping, the omega squared isn't going to change. The omega squared is still 256 here. So how does lambda squared and omega squared compare here? The lambda squared is less than the omega squared. Lambda squared minus omega squared is going to be negative 192. And whenever that happens, that means that we're going to have, since lambda squared minus omega squared was the term inside of the square root for the roots of the auxiliary equation, that means we have a negative square root, and that means we have complex roots. That means this is what we call an underdamped system. The damping factor, the lambda squared, is not as strong as the force coming from the spring constant omega squared. So that means we're going to get some oscillation in this system because it's underdamped. When you apply the initial conditions, you're going to find out that this equation of motion here, see if we can bring it up here. I want to scroll down a little bit if my system will let me. There we go. Remember, in an underdamped situation, our solutions are exponentials times sines and cosines. The exponential here, the damping factor at the beginning is always e to the negative lambda t. And remember, we found out earlier that lambda was 8. So e to the negative 8 t, or here in my Desmos, I've written it as e to the minus 8x, but we would usually say e to the minus 8t. That's our damping factor. And that's going to ensure that ultimately the motion of this object moves towards equilibrium. It moves towards 0. But while it's moving towards 0, it's going to do that in an oscillatory fashion. We have some sines and cosines. When you take a look at what is the square root of omega squared minus lambda squared, that's the square root of 192. And since 192 is 64 times 3, the square root of 192 is actually the same thing as 8 times root 3. So we get factors of the cosine of 8 root 3 times our independent variable and sine of 8 times root 3 times our independent variable. That's coming from the square root of this number 192. These constants here, 2 for C1 and 13 root 3 over the square over 13 root 3 over 24, those come from applying the initial conditions for this particular problem. Again, I'll leave that as an exercise, a fun exercise to you to verify that those are the correct constants C1 and C2 that match the initial conditions that we had. But the key idea here is that we have this underdamped situation where our solutions are exponentials, negative exponentials, times sines or cosines. And because we have those sines and cosines, notice that when I've graphed it out here, we're going to see some oscillatory behavior. Starts down, passes through the equilibrium point, reaches a point here. Now this point here is actually, because it's negative, it actually is above the equilibrium point. So it's gone above the equilibrium, and now it's coming back to the equilibrium as I'm tracing it out on the graph here. And then it goes back below the equilibrium, comes back to the equilibrium, and goes below it. And here we kind of lose the graph a little bit because it's so close to 0 at that point. But it's continuing to oscillate back and forth. closer to zero. If we were to zoom in on that, we would see those oscillations continuing as it moves towards its equilibrium position. So was a case of underdamped motion, uh, oscillatory behavior with the system eventually moving closer and closer to the equilibrium point. So I hope that example has been informative as we took a look at first reviewing um, free undamped motion, and then we applied some damping to see what would happen. In our next video, video number 4, we're going to take a look at another scenario of damped motion and analyze it and see whether we get underdamped or overdamped or critically damped behavior from the system. So tune in soon for video number 4 from our sequence on applications of second order differential equations.